In this video, we're going to be going through a few problems from the Chapter 2 review. Emphasis on a few problems. So once again, just like the Chapter 1 review, we're not going to go through all of them. We're just going to hit a few of the problems, ones that I think that are worth talking about some more. A lot of the other problems that you might see on the review, if we don't hit it, there's a good chance that we go through a problem similar to it in one of the other videos. So I'd encourage you to kind of watch through those videos just to kind of double check those again. I am going to try and hit a few more problems in the last review video, but just not spend as much time on each problem. So for example, I wanted to start talking about numbers 3 and number 7 from the review. Both of these questions are similar. Number 3, all it's asking you to do is find the relative extreme points. What do I mean by relative extreme points? I'm talking about minimums and maximums. So that's all this one's talking about, is find the minimums and maximums. Okay. Number 7 is one of the problems where you are then going to say, find the coordinates of the minimums and maximums, find the points of inflection, state where the function is increasing, decreasing, as well as concave up, concave down. This is one of those problems. Number 7 is one of those problems where we're gonna answer those 7 questions, right? Increasing, decreasing, minimums, maximums, concave up, concave down, and points of inflection. Both of these are similar though, because of course, what's my first step in either of these problems? I need to find the first derivative. The first derivative is going to tell me about minimums, maximums, and increasing, decreasing. So my first step is going to be take the first derivative. Well, in both of these cases, so if I take this derivative, I get negative 2/3 x to the negative 1/3. Okay, and in this case, in number 7's case, I get negative 6/5 x minus 2 to the negative 3/5. If you have questions about those derivatives, maybe rewatch some of the chain rule videos from chapter 1 or power rule videos, or talk to me and we can kind of go through some of these. But that's what I get for the derivatives. And these ones are both unique because if I were to rewrite this, I would have negative 2 over 3 times the cube root of x. And then this one would be negative 6 over 5 times x minus 2 to the 3/5, right? That negative exponent means it goes in the denominator. Now, if I'm finding relative extrema or critical points, if I'm finding my critical points, what do I want to do with this derivative? I want to set it equal to 0. I want to set these derivatives equal to 0. But if I tried to solve this, I actually wouldn't get any answer out. Most of these relative extrema problems, most of these minimum maximums problems, you're going to be able to solve this just fine, right? You're set your derivative equal to 0 and solve, see what x values will make this 0. But these are a couple of special cases where when I set this equal to 0, it turns out there's no x value that will make this 0. So this is where we have to remember. Critical points occur when the derivative is equal to 0 or is undefined. So that's kind of the big idea that I wanted to make sure and talk about with these two problems. Is please remember that these functions also have critical points wherever the derivative is undefined. So if I look at number 3, what x value is going to make this undefined? X equals 0. Right? If you try and plug in 0, you get a 0 in the denominator and your derivative is undefined. Okay? Over here, number 7, what value, if I plug it in, gives me an undefined derivative? Well, it turns out x equals 2 will do that, right? 2 minus 2 gives me a 0 in the denominator, and so my derivative is undefined. So those also count as critical points. Your minimums and maximums, your relative extrema, can occur at these points as well. So something to keep in mind. With number 7, you'll have to keep going, of course, after you figure out minimum, maximum, increasing, decreasing, you're going to have to find the second derivative. The second derivative is going to be very similar, where if you try and set it equal to 0, you're not going to be able to solve for anything. The only possible points of inflection you're going to get are whatever makes the denominator equal to 0. Okay, next, let's look at number 9. Number 9 is all about absolute maximums and minimums, absolute extrema. So I just wanted to talk about this one just to remind you of when we're looking at absolute extrema, there's some different places that we need to look. Okay, I'm still going to go through the same process that I've been doing for the last few problems. I still want to take the derivative and set it equal to 0. Okay, why? Because my absolute extrema can occur at my local minimums or my local maximums. These local extrema can also be your absolute extrema. If I have a local min, it could also be my absolute minimum. And so I'm still going to take the derivative, set it equal to 0, and solve. For this problem, I'm going to get 3x squared equals 3, divide by 3, I get x squared equals to 1, and I get x equal to positive or negative 1. Don't forget that when you take the square root as a part of the solving process, you have to look at both the positive and the negative values. So these are my critical points. But with these type of problems, if you remember, usually they'll give you an interval. I forgot to here, but my interval for this problem is from -4 to 1. Why is an interval necessary? Because if you don't have an interval, your absolute maximum or your absolute minimum may not exist. You may not have an absolute max or an absolute min. If your function goes up to positive infinity, you don't have an absolute maximum. So in this problem, my bounds are from -4 to 1. Okay? So if we remember, where can my absolute minimums and maximums occur? Well, they can occur at my critical points, but they can also occur at my endpoints. So, to figure out my absolute extrema, I'm going to test those 3 points. -4. Why do I say 3 points? Because one of my critical points is one of my endpoints. Do you notice that? One of my critical points is +1. Well, that's one of your endpoints anyway. So I'm going to test -4, -1, and +1. Okay. What do I mean by test? Well, before in my process for like number 7, if I'm testing to see whether something's a local min or a local max, a lot of the times we'll use that first derivative test where I'll put my critical points on the number line and then I'll test the intervals in between. And the point of that is figuring out if I'm increasing and then decreasing or decreasing and then increasing. But because I'm looking for absolute min or absolute max, I'm really just concerned about which x value is going to give me my absolute highest y value, and which x value is going to give me my absolute lowest y value. In that case, to test these points, I'm just going to plug them back into my original function. So, -4 cubed minus 3 times -4. Well, let's see. 4 cubed gives me 256, or -256, plus 12. So I get -244. If I plug in -1, I get -1 cubed minus 3 times -1, which is equal to -1 plus 3, which is equal to +2. If I plug in +1, I get 1 cubed minus 3 times 1, which equals 1 minus 3, which is equal to -2. What does this tell me? I have a absolute max at -1, and I have a absolute minimum at -4. Okay. Careful though, because like I said, if you move on to number 10, you'll notice number 10 does not give you an interval. We were able to find an absolute minimum and an absolute maximum for this problem because I had a specific interval from -4 to 1. If I don't have a specific interval, there's a good chance that either there's no absolute maximum or there's no absolute minimum, or that there's neither, that you can't find the absolute maximum or an absolute minimum. So keep that in mind as you look at number 10. Okay, let's look at number 12. So with number 12, I just wanted to kind of quickly go through the process of optimization again. So in this problem, we're trying to maximize Q, which is some product of two different positive numbers. Notice x must be greater than 0 and y must be greater than 0. So x times y. Such that x plus 28 over 3 y squared must equal 7. So here's my constraint, right? Here's my constraint. I missed an S. This is what's going to limit our values. Okay, it's my limitation. Remember, this idea of optimization boils down to the fact that we're finding a maximum, right? We're finding a maximum, which means the process is going to be very similar. I'm going to take the derivative, set it equal to 0. The issue is I can't take the derivative yet because I have it in terms of two different variables. So before I can take the derivative of this Q function, I need to get it all in terms of one variable. That's where the constraint comes in, okay? What I can do with this constraint is I can solve this constraint for one of my variables. My suggestion would be solve for x. Don't solve for y. That's going to make this way too complicated. So I'm going to solve for x just by simply subtracting 28 over 3 times y squared to the other side. So I get 7 minus 28 thirds y squared. What that allows me to do is I now can come back here and plug that in for x. Okay, I can simplify by distributing. And now I'm ready to take my derivative. Okay, right? Because now it's all in terms of one variable, so I can go ahead and take the derivative in terms of y. So Q prime is equal to 7 minus, I'm going to bring down that 3, and I get 28 times 3 divided by 3. Well, that just leaves me with 28 y squared. Okay? Now I can solve for y. Okay? Oh, wait. Solve for y. How? Because once again, once I take that derivative, I'm going to set it equal to 0. Set it equal to 0. So that gives me 7 equals 28y squared. Divide by 28, I get 1/4 equals y squared. Take the square root, and I get y is equal to positive or negative 1/2. Square root of 1/4 is 1/2. Okay. Now notice I said positive or negative, but based off of our assumptions, what has to be true about y? It has to be positive. So I can go ahead and get rid of the negative option. So y is equal to positive 1/2. Okay. To figure out what x is, I can just plug this in. Plug that in to this function. And that'll give you what x is. So that's kind of my basic process for optimization. Write out your equation. Before you take the derivative, make sure it's all in terms of one variable. If it's not, figure out what your constraints are, what your limitations are, and use those to get it all in terms of one variable. Okay, very nice. Real quick, so the other optimization ones might look familiar. 13's new, but if you draw a picture, that's going to help you. Okay, draw a picture, and you'll see that the river is one side of your pen that you're creating. So when I talk about perimeter, I just have 2 widths and 1 length to factor into that perimeter. I don't have to put one at that bottom length for the river. Okay. Number 17 is also another optimization problem technically, But what's nice about number 17 is it's all in terms of one variable already. So you don't have to worry about any constraints or limitations. This one's just as simple as writing your profit equation by doing your revenue minus your cost. The tricky thing about this one, though, is just read that blue text. Do not round until the final answer, then round to the whole number as needed. Your answers are going to come out as these big decimals, though. So how does that work if you're rounding to a whole number? Just be careful about the units. Your revenue and cost are both in thousands of dollars, and X is in thousands of units. So with number 17, you're probably going to get out some answer of like 1.00573 or something. And what we have to recognize is this is thousands of units. So I'm going to move that decimal place 3 times. And so that tells me, 1,000, and if I round to the nearest whole, 1,006 units. Okay, so that's what's tricky about this is not 17, this is 14. So that's what's tricky about 14. The math behind it is simple enough, but inputting your answer gets a little tricky and confusing. So just make sure you're very careful about inputting your answer on this one. Okay, so now I want to talk about number 16. 16 is a great example of differential, so that's why I wanted to talk about this one. Part A is simple enough. Part A is just asking for the profit equation, which of course is just cost minus revenue. No, sorry, whoa. Revenue minus cost. Okay, so I just do 3x minus 0.01x squared minus 1.4x minus 20. Notice how I'm minusing each of those terms because I'm minusing the whole cost equation. I can, of course, simplify that, and I get negative 0.01x squared plus 1.6x minus 20. So there's my profit equation. But B is where I wanted to focus. Okay, because B asked me, find delta P, or change in P, and P prime of X when X is equal to 80, when I'm producing 80 units, and delta X is equal to 1. Okay, so if I'm producing 80 units and I want to change it by 1, and I want to produce 1 more, well, P prime is simple enough, right? P prime, I know what that means. P prime is the derivative. So let me go ahead and calculate the derivative here. I get negative 0.02x plus 1.6, right? That's me just using the power rule. Negative 0.01 times 2, when I bring down that 2 power, gives me negative 0.02, x to the first, plus 1.6. Okay. Now, you'll notice, though, it does say find P prime of X when X equals 80. So what does that mean? That just means I now need to plug in 80 into my derivative and see what I get. Okay. But then it asked me to find delta P. Delta P is very different. If you remember from our video about this, delta P means the actual change in P. If I go from producing 80 units to producing 80, delta X is 1, that means I'm increasing it by 1. So go from producing 80 units to 81. What am I going to use to help me out with that? I'm going to use my original profit equation. So to find delta P, I need to know what's my profit for 80 units. So I'll plug in 80 to my original equation and see what I get. Okay, well, negative 0.01 times 80 squared gives me negative 64. Ooh, sorry. And then 1.6 times 80 gives me 128. Minus 20, I end up with 44. So that's my profit when I produce 80 units. And then I need to see what my profit is if I produce just 1 more unit. this involves just me plugging in 81 and seeing what I get. Okay, I get, let's see, when I do that first term, I get negative 65.61. When I do that middle term, I get 129.6 minus 20. I end up with 43.99. So, what's my delta P? How did my P change? Well, my P changed by going down by, so negative 0.01. Do we see that? I went from 44 to 43.99, so my profit went down. Thus, my delta P is negative. How much did it go down by? By just 0.01, by 1/100th. And there's my delta P. Okay, and I guarantee you this P prime of 80 is going to be pretty close. It's going to be pretty close to your delta P, but the process of getting the two is very, very different. Okay, the last problem I want to spend a good amount of time on is number 19. The rest of them, past number 19, there's a few elasticity problems and, of course, a few implicit differentiation problems. We've gone over those ones fairly recently, and I felt like they were pretty straightforward. So if you have questions on them, feel free to ask me, but hopefully those ones you can kind of figure out on or using our previous videos or by using the aids in Pearson. I will say for the implicit differentiation functions, please remember that product rule is necessary. Okay, for a lot of those, you're going to need product rule as you take those derivatives. But let's look at number 19. We're going to use this differentials idea, okay, that I can estimate my actual change in y using the derivative if I know the change in x, okay, in order to estimate the cube root of 64.46. Now, I can't remember if I did a problem like this in class, in one of my videos. But the reason why this is helpful is because the computing power to calculate the cube root of 64.46 is enormous. That is a very complicated number that ends up being irrational. But if I take a close look, this is actually really close to the cube root of 64. Well, what's nice about the cube root of 64? I know what the cube root of 64 is. The cube root of 64 is 4. So with that in mind, what I can do is I can come back to this idea that we just talked about, and what I'll say is I'm going to say, let's let x equal 64. Why do I want x to equal 64? Because if I cube root 64, I get a nice clean number. 64 is a perfect cube. And it's a perfect cube that's close to the number that I'm trying to approximate. So with that in mind, if I'm trying to approximate 64.46, what does that make delta x? How far away is 64.46 to my preferred number? Delta x is 0.46. Right? That's the difference between what I do have and what I want to have. Okay. So I'm halfway there, right? I have my delta x, but I now still need to calculate what f prime of x is. Okay. Well, what is f of x in this case? Okay. F of x in this case is what function am I actually applying? What am I actually doing to this number? So my f of x, actually I'll just keep using black. My f of x is cube root of x. Right? That's what I'm actually doing to this number. That's my function. So I need to know what f prime of x is. Remember, I can rewrite this cube root of x is just x to the 1/3. That makes finding the derivative a lot more straightforward. My derivative is just 1/3 x to the negative 2/3. Okay, so there's my derivative. But if I'm using this derivative to approximate what delta y is for this specific delta x, what x value am I going to plug into my derivative? I'm going to plug in this x value. right? The reason why I want to plug in this x value is because I actually know what 64 to the negative 2/3 is. That's a simple calculation that I can do without a calculator, right? Because I can rewrite this as 1 over 3 x, x to the 2/3 is the cube root of x squared, right? Or conversely, in fact, it makes it a little bit nicer for our equation. It's the cube root of x all squared, right? You can choose what order those two things go in. If I plug 64 into this, okay, so f prime of 64, I get 1 over 3 times the cube root of 64 squared. I know what the cube root of 64 is, right? We already talked about that. That's the reason why I like this number of 64. So what do I get out of this? I get 1 over 3 times cube root of 64 is 4 times 4 squared. And so that leaves me with 1 over 48. So that takes care of my second half. That right there is my f prime of x. I've now found the derivative at 64. I'm going to use that derivative to estimate what delta y is. Okay, delta y is equal to f prime at 64, so 148, times what my delta x is. If I multiply those two things together, I get 0.0095, and I think repeated 3s. Okay. How does this help me estimate the cube root of 64.46? Okay. This helps me because what is this? This tells me that the difference, right, delta, the difference between the actual value of the cube root of 64.46 and the value if I just do the cube root of 64 is about this much. So to get my decimal approximation, cube root of 64.46 is approximately my value of the cube root of 64 plus the change, 0.009533. So I get 4.009533 repeated. And the problem does say round to 3 decimal places. So there's my 3 decimal places. What does this 5 tell me to do? It tells me to round it up. So I get 4.010. So the cube root of 64.46 is approximately 4.01. Okay, if you have any other questions about any other problems on the review, please reach out as you guys prepare for the exam. Remember that the exam, because of President's Day weekend, the exam is open all the way through Tuesday evening, a week. So all of this week and then through the next Tuesday, February 20th. Best of luck, and I'll talk to you next week.